Hello everyone, my name is Changcheng. I'm working with Dr. Koshi and Dr. Ravi. Today I'm going to introduce you electrical discharge machining of superhydrophobic surfaces. I still remember it was about 3-4 years ago, after Christmas. I came back from China and I landed at Pearson Airport. It was extremely cold, just like this Christmas. And all the passengers stayed in their airplane for about an hour because they said the gate was frozen and they had to do de-icing for the gate. Obviously, I didn't take this picture because I was in the airplane. After several years, I met Dr. Koshi for my master position, and he introduced me my research topic, which was about superhydrophobic surfaces. Then I suddenly realized, wow, that could be a solution for my airplane problem. So, what exactly is a superhydrophobic surface? And how is it going to be helpful for the frozen gate? So first of all, let's look at the picture. This is a lotus leaf, and we can see some water drops on the lotus leaf, and they are almost in spherical shape. This was the origin of a superhydrophobic idea. And firstly, I'm going to introduce you a really important term, which is called contact angle. So if we have a surface, and we put a water drop onto the surface, we do a tangent line to the water drop, and this angle is called contact angle. And if this angle is bigger or equal to 150 degrees, then we say this surface is superhydrophobic. And there is another important term, which is called tilt angle. So when we tilt the surface, the water drop will roll off. And for a superhydrophobic surface, this angle is always smaller or equal to 10 degrees. And this phenomenon we call lotus effect, because it was from lotus leaves. We have another picture here. If we look closer under a microscope, we can see many big bumps on the surface, and they are in microscale. And if we look even more closer to each single bump, we can see thousands of little arms, and they are in nanoscale. So basically, we have a lotus leaf surface. We have many big bumps on the surface, and we have thousands of little arms. And for this structure, we call it hierarchical structure. And the hierarchical structure will help the surface to hold a water drop in a spherical shape and to prevent the water drop from spreading. And also we can see this hierarchical structure will help the water drop to trap air underneath so that the water drop can be slippery on the surface. Let's keep everything in mind and take a break from here. Let's take a look at our fabrication technology, which is electrical discharge machining, or we call it EDM. So what is EDM? Let's start from a video. We can see the top part is moving up and down, and that's the tool of our machining process, or we call it electrode. And the bottom is the workpiece, and they are fully immersed in a kind of dielectric liquid. In our case, it's hydrocarbon oil. And if you look more carefully, you can see some film generated. And that's the material removed from the process. And in the middle, we can see some lights, and those are the sparks. So generally, we have a workpiece at the bottom, and we have an electrode at the top, and they're fully immersed in dielectric oil, and we have a flushing on the side. And the whole thing is connected in an electrical circuit, and now we can see it is an open circuit. And at the moment, the electrode is carrying positive charge, and the workpiece is carrying negative charge. And then the electrode will move towards the workpiece, and the voltage will overcome this little gap, and it will generate sparks. Those sparks have really high temperature, around 6,000 to 8,000 degrees C, which will melt away some material from both the workpiece and the electrode. And the duration of each spark is really short, in microseconds. That means at the moment you blink your eyes, the machine already generates thousands or even millions of sparks. And those sparks, they don't come together, but they come one by one. That's why we have a flushing on the side. After the previous spark, there will be some debris particles in the gap, and the flushing will just flush away all of them so that it will make sure the next spark will be generated without any disturbance. And then after the entire process, the electrode will move backward. And then the flushing will go through the entire space, and it will just clean everything. so that the machine will start the next cycle of sparks. So this is the motion of an EDM process. So why did we pick EDM to fabricate superhydrophobic surfaces? Let's take a look at the surface first. The blues are the valleys and the yellows are the peaks. And if we take a look at the cross-section of the surface, this is what we can see. And the top surface has many craters. And the shape of those craters can be determined by two parameters. One is current, and the other one is the duration of the sparks, or we call it on time. Bigger the current, deeper the craters, and bigger the on time, wider the craters. And if we do a distribution analysis for the surface head in terms of frequency, by the way, the surface head is the distance from the bottom surface to the top surface. And the distribution will be like this. This means an EDM surface has a positive screwness. And the positive screwness will help the water drop to trap air underneath in those craters. And also we can see those peaks. They will help to hold the water drop and to reduce the contact between the water drop and the surface so that it will make the water drop more slippery on the surface. And if we go back to our workpiece, we zoom into the top surface, we generate some big sparks and we'll create some big craters. We call it primary texturing. And then we decrease the energy of the sparks. We will generate some smaller craters and we call it secondary texturing. And with both of them, we'll have our EDM hierarchical structure. And now let's take a look at our measurement. This is the setup that I'm using all the time. The left side is a camera, and in the middle, this is the stage. And at the top, there is a needle that is dispensing water drop. And at the back, this is the light source. So through the camera, this is what we can see, a needle that is dispensing a water drop onto the EDM surface. For our preliminary results, the material we are using is aluminum 7075. And for a polished surface, or we say a flat surface, we can get a contact angle around 83 degrees. And if we do our primary texture only, we can increase the contact angle around 116. And with our hierarchical structure, we will have a contact angle around 150. And there are two videos that will show you the water drop behavior without EDM texturing and with EDM texturing. First of all, without EDM texturing, we can see the water drop will just stay on the surface, and the surface is just like a regular surface. But with EDM texturing, the water drop and the surface, they don't like each other. When water drop comes to the surface, it will be just bounced off or repelled from the surface. And there are also many other fabrication technologies like lithography and etching, electrochemical polymerization, and some other methods. And there is a common problem for all of them, which is that the material they're using are polymers or some colloidal materials which are soft. So they can be really easily damaged by some mechanical strength, even the rainfall. That's why we pick aluminum 7075, because we want to fabricate a robust metallic superhydrophobic surface. There's another competing technology, and they use laser texturing to create this kind of grid pattern on a copper surface. But the limitation for this technology is that in order to fabricate a surface in 10 by 10, like this big, they need to spend about 5 hours. 5 hours means 300 minutes. But for our EDM method, we only need 1 minute. So 300 to 1, that's the difference. Now the problem is solved. If water drop cannot stay on a surface, neither ice, then we don't need to worry about the frozen gate anymore. We can just get off the airplane easily and fast. Thank you.